Take a look at this. It's a handwritten digit, a simple 3. For us, recognizing it is effortless, instantaneous. But what does it mean for a computer to recognize this 3? How does it transform these squiggly lines into the abstract concept of a number? This isn't just a theoretical question. It's the fundamental challenge at the heart of countless AI applications, from reading checks to self-driving cars. And understanding how a computer does this is the first step to building your own intelligent systems. In this series, we're diving deep into the foundational concepts of AI and machine learning. Not just what they are, but why they work the way they do. Because when you truly grasp these building blocks, you unlock the power to create your own incredible weekend projects. So, let's go back to our 3. A computer doesn't see an image, it sees numbers. Imagine our handwritten 3 is drawn on a tiny grid, say, 28 pixels by 28 pixels. Each of these 784 pixels can be represented by a number. For a grayscale image, a pixel's value might range from 0 for pure black to 255 for pure white. To make things simpler for our computer, we often normalize these values to be between 0 and 1. So, a black pixel is 0, a white pixel is 1, and shades of gray are somewhere in between. This collection of 784 numbers is our input. It's the raw data the computer has to work with. We can think of each pixel's value as an individual input neuron in our network. But how do we go from 784 numbers to the decision that this is a 3? We need a way to combine and process these inputs to find meaningful patterns. The simplest way to combine numbers is through multiplication and addition. Imagine we want to detect if there's a vertical line in a specific part of our image. We can assign a weight to each of these input pixels. Pixels that are part of a vertical line would get a higher weight, while pixels outside it would get a lower weight. We then multiply each pixel's value by its corresponding weight and sum them all up. This weighted sum tells us how strongly that vertical line pattern is present in that specific area. But what if the sum is always positive, even when the pattern isn't very strong? We need a way to shift this sum, to set a baseline or a threshold. This is where the bias comes in. The bias is just another number that we add to our weighted sum. It allows our neuron to activate more easily or less easily, regardless of the input. So, for each of our neurons in the next layer, we calculate a weighted sum of its inputs, and then add a bias. This gives us a single number. But why do we need anything more? Why can't we just keep doing weighted sums and biases? The problem is, if we only use multiplication and addition, no matter how many layers we stack, we're essentially just doing one big linear operation. It's like trying to draw a complex curve using only straight lines. To learn truly complex patterns, like the intricate loops of a 3 or the distinct features of a 7, we need nonlinearity. We need to introduce a bend or a curve into our calculations. This bend is introduced by something called an activation function. After we calculate our weighted sum plus bias, we pass that result through this function. One common activation function is the sigmoid function. It takes any number and squashes it into a value between 0 and 1. Small inputs become close to 0, large inputs become close to 1, and intermediate inputs get a smooth, nonlinear transformation. So, our neuron's final output isn't just the weighted sum plus bias, it's the result of passing that sum through an activation function. This output then becomes an input for the next layer of neurons. Now, imagine we have many such neurons, each looking for different patterns, some for vertical lines, some for horizontal, some for curves. These form our hidden layer. Each neuron in this hidden layer takes all 784 input pixels, applies its own set of weights and its own bias, and then passes the result through an activation function. This is the core operation: output equals activation, input times weights, plus bias. The input is our pixel values. The weights are the numbers that determine the importance of each input for a specific neuron. The bias is an adjustable offset. And the activation function introduces nonlinearity. Finally, we need an output. For recognizing digits 0 through 9, we need 10 possible outcomes. So, our final layer will have 10 neurons. Each of these 10 output neurons takes inputs from all the neurons in the hidden layer, applies its own weights and bias, and then an activation function. The activation function for the output layer is often different, like softmax, which ensures all 10 outputs sum up to 1, giving us probabilities. So, if our network is confident it's a 3, the neuron corresponding to 3 will have a high value, say 0.95, while others will be very low. Let's put it all together. Our handwritten 3 starts as 784 pixel values. These values flow into the first hidden layer, where each neuron performs a weighted sum, adds a bias, and applies an activation function. The outputs from the first hidden layer then become inputs for the next layer, and so on, until they reach the final output layer. The neuron with the highest probability in the output layer is the network's guess. In our case, it's the 3 neuron, with 95% confidence. Now, imagine trying to do this by hand. For our tiny 28 by 28 image, with just one hidden layer of 16 neurons, and 10 output neurons, that's 784 inputs times 16 weights for each hidden neuron, plus 16 biases. Then 16 hidden outputs times 10 weights for each output neuron, plus 10 biases. That's over 12,000 individual weights and biases. And this is a tiny network. Modern networks have millions, even billions, of these parameters. The beauty of this system is that the network learns these weights and biases automatically from data. We don't tell it what a 3 looks like, we show it thousands of 3s and 0s and 1s, and it figures out the patterns itself. It learns to detect edges, then corners, then curves, then combinations of these features, until it can confidently distinguish between a 3 and an 8, even if they look very similar to the human eye.